Hello students, myself Dinesh Kumar, and in today's lecture we'll be discussing about collision resolution techniques, right? So this is agenda for the today's class. We'll see what collisions are, what are the various methods like separate chaining method, open addressing. Under this heading of open addressing method, we'll see linear probing, quadratic probing, double hashing, right? So let's start. So first one is collisions. See, in the previous lecture when we started hashing, we said we have already discussed various hashing function like division modulo method, like mid-square method, and but we said this that there is no such hashing function which can 100% avoid the collisions. Collision is means like given two different keys, and your hash function maps the two different keys to the same location in the hash table, right? That is when we call a collision has occurred, and we need to take certain actions to avoid that collision, to deal with that collision, right? So what we actually do is we always try to minimize the number of collision. We choose hash function in such a way that the number of collision can be minimized, right? Like we always choose a size of the table which is a prime number, and that prime number should not be close to 2 raised to power k, right? So but when collision sometimes occurs in spite of everything, right? No hash function can guarantee zero collisions, right? Collision occurs when a hash function maps two different keys to the same location, right? So two records cannot be stored in the same location, we all know that, so we simply say collision has occurred, and the collision resolution techniques need to be followed when a collision has occurred, right? So there are two popular methods for resolving a collision. One is separate chaining, also called open hashing. Separate chaining is also called open hashing method, and another one is called open addressing. Open addressing is also called closed hashing. See, in case of closed hashing, we have three methods. One is called linear probing, one is called quadratic probing, and one is called double hashing. Now all these methods have their advantage and disadvantage. Some is better in some case, other one is doing good in other case, right? So we'll see them one by one and understand how they actually resolve the collision, right? So there are two popular approach. One is the separate chaining, right? So let's see. So first one is the collision resolution by the separate chaining. See, whenever in case of separate chaining method, collision can be resolved by creating a list of keys that map to the same value. So what we do is when a key is mapped to a memory location which is already occupied, then what we'll do is we actually create a linked list in that particular memory location, something like this. For example, let's suppose some key, let's suppose this is your hash table, okay? This is your hash table starting from some address location 1 2 up to some n, right? And let's suppose some key k1, is already stored, right, by the hash function, and that k1 will be stored at this particular location. Now the second key k2 is also mapped onto this index a1. Then what we need to do is we simply create a linked list over here such that k2 will also be stored here, okay? K2 will also be stored here. So such type of linked lists are there in case of separate chaining method. In case of separate chaining, we actually create a list of keys that map to the same value, same index value, right? For example, in our case, these two, one is k1 and another one is k2, they map to the same index, that is 1. So what we'll do is we create a chain of such key values, right? In chaining, each location in the hash table stores a pointer to a linked list. Each location stores a pointer to a linked list that contain all key values that were hashed to the same location. You got my point? See, this something like this. For example, in this particular case, this k1 and this k4, two different keys, they are mapped by the your hash function to the same location, this particular location. So this particular location contains a pointer to the linked list. So where first k1 is stored, and then the next of k1 is store the address of another node where k4 is stored. If some other key is also mapped to this particular location, that and then a new pointer will be created and a new node will be created, and something like this. Like let's suppose it is k9. So k9 will be stored like this, and this will contain null. Okay? So this is what we call collision resolution by chaining method, right? Separate chaining method. Okay, let's understand this with the help of example. See, collision resolution by chaining. See, in this case, what we are given some set of key values, like these are the key values. Total 7 key values are there in this case. In this order, in a hash table of size 10. So the m in our case is the size of the table. M in our case is 7. Now using chaining with the hash function is given. See, which hash function is this? Hash function is modulo division method. Okay, where the hash function is given key, we simply divide it by the m. M is the size of the table, and whatever remainder comes, we'll use that remainder as a index in the hash function, hash table, right? So let's suppose in our case it is something like this. Okay, so we have location how many? 0, this is 1, this is 2, this is 3, 4. So let's mark this 1 2 0 1 2 3 4 5 and 6. Okay, so these are the locations. So now let's see this, how we can store these values into our hash. How can we map this? See, first value is 23, so we want to map this 23 into the hash table using this. So first we are using which method? We are using division modulo method. So we are doing 23, this is the key, modulo 7 is the table size, so we'll get 2. So this 23 will be stored at location this 23 will be stored at location this, right? Second is 13 will be stored at location this, right? Then we have 21 will be stored at location 0, right? Then we have 14 will also be, see in here it for this it will say again store this at location 0. So 0 is already occupied, so what we'll do is we simply say that here we store 14 and okay, and this is contain null. See, next is we have 7. For 7 it is again giving a collision, so it means 7 will also be stored at this particular location. So what we do now, we'll create a new node, we'll store 7 here, and this next part is contain null. Okay, so this is your linked list is created like this. So next is 8. For 8 storing, we have a location 1, so 8 will go, 8 is unoccupied, so 8 can be stored here. Then again we have a 15. For 15 it again gives a address 1, so 1 is occupied. So what we need to do is create a linked list. Key value will be stored at 15, so 15 will be stored like this, and this will contain null. So this way we handle the collision using collision resolution by separate chaining. See, advantage of separate chaining is the hash table size is unlimited. In this case, you don't need to expand the table and recreate a hash function, because any number of keys, if they are mapped to the same location, you can create any number of nodes. You can add any number of nodes, and all those keys can be stored. So maximum if the collision handling is simple, right? Because you simply are adding new node to the linked list. Just insert a colliding records into a linked list, right? And disadvantages are that using pointers slows the algorithm. Time required to allocate new nodes, right? Second disadvantage is the main cost of chaining is the extra memory is required to store the addresses in the linked list, right? And overhead of multiple linked lists. So many linked lists you need to maintain, right? So these are the advantages and disadvantages of your separate chaining method, right? Next is your collision resolution by the open addressing. See, in case of open addressing, once a collision takes place, once a collision takes place, open addressing computes the new positions, right? New position based on certain mechanisms, right? These new positions which we are talking about are using a probe sequence. Probe sequence means you look for some other location where the colliding record can be stored, and the next record is stored in that particular position. So whenever a collision occurs, we look for the another new address where the colliding record can be stored, right? The hash table contain two types of values. Initially, the sentinel values means to represent that this particular value is not occupied. Okay, this is already free. So the presence of sentinel value, we represent it by -1, indicates that the location contains no data value present but can be used to hold a value, right? There are three main methods which use this technique, open addressing. One is called linear probing, one is quadratic probing, and last one is your double hashing, right? We'll see one by one. So first one is the linear probing. See, in case of linear probing, this is the simplest method to resolve a collision, right? Hash function used in this particular case is to resolve the collision is, see this, hk of I is equal to h dash of k plus I, and mod m, where m is again the size of the hash table. H dash of k is equal to k mod m. This is the your original hash function and will be used when no collision occurs. But if the collision occurs, then we'll use this new to find the new space to store the colliding record. And what is I in this case? I is the number of probe. It starts from 0 to m minus 1. Probe number varies from 0 to m minus 1. M is the size of the table. We'll see this by an example, right? For example, this. Now this is a, let's suppose we have a hash table of size 10. Using a linear probing, we want to insert these keys. We have this key 72, 24, this key. Initially, see this 0 to 9. Our table is see this 0 to 9. These are the addresses of our array, right? So because size of the table is 10, so and all locations are available to store the values. Like initially, first key is, see this first key is your 72. So 72 is the first key which we want to store, and we want to calculate its address. Is, see this 72. This is the key. Okay, h of k 72 mod 10. 10 is the table side plus I is because it is the first probe 0, right? And finally mod 10. So 72 mod 10 plus 0 mod 10. It is equal to 2. So 2 location is empty, right? 2 location is empty. It is available for storing some value. So this no collision in this particular case. So 72 can be stored. See this. See this. 72 is stored in this particular location too, right? Because here no collision has occurred, right? Now see this second value is our 24. For 24 again we apply the same hash function, and in this case also it will give a location 4. So we'll go to a location 4 in this particular case. Earlier it has a -1, so now we'll store 24 at its place. So in this particular case also no collision occurs, right? So we'll see another. Now we want to store 63. Again we apply the same hash function, right? So we'll come with the 3 value. Third location is free, hence we store the 63 at its index 3, right? Then comes 81. For 81 also we apply this same hash function. Hash function is, this is h dash of k, original hash function, plus this value is nothing. This value is the I. Okay, I is the probe, because first time we are looking for some space to store this 81, right? So 81 mod 10 is 1 plus 0 is 1, so it comes out to be 1. So location 1 is free, it is vacant, so we can always store 81 in this. So again no collision has occurred till now. Now in this case, now next key we want to store is 92. For 92 we have come with the index which is calculated using this hash function is 2. Now when you look at the value 2, see this is the index 2, and this value is already occupied by some other key value which is 72. If it is -1 is there, a sentinel value is there, it means that location is free. But now 72 is there, so it means this location is already occupied, means collision has occurred, right? So if a collision has occurred, then we again need to apply the same function, but instead of this 0, what we need to have is, we need to have 1, because the probe is the second probe. Okay, the probe is the second probe. So we will see how. See this now, instead of this, now we have the 1. Okay, we have 1 because this is the second. Instead of I initially it is 1, now it is I initially it is 0, now it is the second probe, so it is 1, right? So now next we have 3, calculated value will be 3. Now again we go to 3, and 3 is already occupied by the 63, so again a collision is there. So we will again apply the same formula with the value of probe I is equal to 2. We have tried with I is equal to 0, collision occur. I try with I is equal to 1, collision has occurred, and try with I is equal to 2, again collision will try this, right? So for I is equal to 2, see this value of I now we have put is 2. See this is why original hash function which we have used earlier also. 92 is the key, 10 is the M mode size, and then this is the I, and divide by again mode 10, right? So we'll be using the remainder. So again it will give the address 4. So again this address 4 is again occupied, right? Again it is occupied, so again a collision has occurred. So we'll try one more time with the I is equal to 3, because it is the third probe, starting from 0, 1, 2, it is the third probe. So now it will see it is giving the index 5, and when we look at the index 5 was empty. That's why we have stored a 92 in this particular case. So in case of linear probing, what we do is, if for example, if for a particular index some collision has occurred, then we look for the empty space in the corresponding sequential positions, right? Look for the empty space in the corresponding sequential position. Now see this, first we have the first index given by this hash function is 2. We have a collision, then we have index function 3, again we have a collision, then we have index function 4, again we have a collision, and then we have index function 5. There is the empty space, and we'll store the 92 at this particular place. Okay, so this way linear probing works, right? Advantage, linear probing enables good memory caching. This is one advantage, and second one is that more the number of collisions, higher the this is the disadvantage. More the number of collisions, higher the probes that are required to find a free location, and lesser is the performance. See, we are looking for the performance that is equal to order of 1. If the number of collisions are more, then the number of probes required is more, right? So the process is known as primary clustering. Primary clustering means all the values which are mapped, which are stored in the hash table, tend to cluster into a small region, right? That is what we call clustering, because once a collision occurs, then the colliding value will be stored in the immediate next location. Again, if a collision occurs, then the colliding value will be stored in the immediate the first free location that will be available. So this is called primary clustering, right? The second method is in this probing method is called, we call it quadratic probing. Instead of linear probing, we do quadratic probing. It actually avoids the problem of primary clustering, right? So in this case, the hash formula is something like this. See this, we have two constants C1 and C2, and then we multiply C1 with I, and we multiply C2 with I square. So it is something like that. It is something like that. This is quadratic probing. It is something like that. You have something like ax square plus bx and plus C, and you know this is what, this is constant value, right? This is the first key, which is first index that will be generated, right? This is simply calculated using this K mod M, where K is the key, M is the size of the table. So this value once calculated, it will be constant, right? So it is quadratic probing. Instead of probing linearly, we'll probe the quadratic way. And this M here, this M is the size of the hash table, we already know, and I is the probe. I is what? I is the probe number that varies from 0 to M minus 1. I is what? I is the probe number that varies from 0 to M minus 1, and C1 and C2 are constant such that they are not equal to 0. Now let's see how quadratic probing works. See, consider again, given a table size of M is equal to 10, and given these two C1 and C2, these are nothing but these are the your constant values given, right? You can assume that both are 1 also, and it depends on, they may be given in the question, value of constant 1 and constant 2, they can be given in the question. So in this case, H dash is equal to K mod M, where M is equal to 10. Initially your hash table look like 6, all the positions are empty, so all positions are available for storing the key values, right? So first one is this is our hash function, quadratic hash function, which we'll be going to use. So first key will be 72. So 72, you put all these value into 72. So first hash function will be, see this part is hash dash of K, simply 72 mod 10. Then this is C1 is equal to 1, C2 is equal to 3, and I, because I is this is the first probe, so I value of I is equal to 0, and finally mod 10, so it comes out to be 2. So location number 2 is free, so we'll store this key 72 into this location, right? Then we have 27. For 27, again we apply the same formula, right? So we'll get the location 7, and location 7, then we go to location 7 in our hash table, and that hash table, this particular value is also free, this index is also free, so we'll store this 27 into this particular location. Then next key will be 36. So for 36, we apply the same formula, we'll get index 6 is also free, we'll store 36 here. Then again we have 24. For 24, we again calculate, see this, you remember this? No, this is your original function, plus this is the C1 constant 1, this is C2 constant 2, this value is I, this value is probe means this is the first probe 0, and the value of this probe goes from 0 to M minus 1, no? So this comes out to be 4. So we'll see that fourth location is free or not. It is free, so that's why we have stored this 24 into this particular. So we have mapped successfully this 24 into this hash table, right? Next is our 63. When we apply 63, so we'll get a index 6, right? So since this is empty, so this 63 will be mapped to this index 3 and without any collision, right? So next one is your 81. Again we apply, and 81 is also added successfully to the location 1, index 1 in the hash table, right? So hash table will look like this. These where we have values other than -1, they are occupied, and where we have sentinel values -1, they are free, right? Now see, now we have the next key value will be 101. Now for 101, if you calculate this, then the index comes out to be 1. Then what we need to do, see this, previously this one location contains 81. So when a new key value 101 is mapped to the index 1, then a collision has occurred. So when a collision has occurred, see this, when T1 is already occupied, so key 101 cannot be stored in T1. Therefore, try again for the next location. Thus, the probe is equal to I is equal to 1. So see this now. This is C1. This is C1, and this is probe. This value is probe. Similarly, this is C2, and this value is probe. Okay, this value is probe. So again, when we calculate this time it comes out to be 5. Now 5 is vacant. See this, 5 is vacant. It was empty. It was not occupied. Earlier it contains -1. So our 101 will be stored in this particular location. 101 will be stored in this particular locations, right? So this way we handle collision using quadratic probing. See this, last time we have address for 101 is 1, next address we have 101 is 5, right? It is not like for after location 1 we are going to location 2, then to 3. That is was in linear probing, but in quadratic probing it is not so, right? So it simply removes the problem of primary clustering, right? So advantages, these are the same advantages. Quadratic probing eliminates the problem of primary clustering and provides good memory caching, right? If there is a collision between two keys, then the same probe sequence, this is the disadvantage, the same probe sequence will be followed for both. This process is called secondary clustering. See, if there is a collision between two keys, then the probe sequence will be same for both of them, right? It will create a not primary clustering, but clusters tends to be spread over the hash table, right? So this is the problem with your quadratic probing. Otherwise it remove the primary clustering problem, right? Then we have double hashing. Double hashing, we use two hash functions rather than a single function. The hash function in case of the double hashing can be given, it is there can be any hash function given, right? So hash formula in this particular case is, see, this is the actual, this is your actual hash function to calculate where the key where this key k is going to be stored, and I is nothing but it is the probe. Okay, m is the, see, this m is nothing but is the size of the table. This h1k is the first hash function, plus I is the probe, h2k is the second hash function. h1k and h2k are two hash function given as like this. h1 is k mod m and h2 is k mod m dash, where m dash is some value which is less than m, right? It can be n minus 1, it can be m minus 2, and so on. And I, this probe number, it always goes from this 0 to m minus 1, right? M dash, which m dash I'm talking about? This m dash. This m dash can be, this m dash is chosen to be less than m. Okay, it can be m minus 1, it can be m minus 2, right? So we apply this hash function, two hash function, more than one hash function, to avoid the collision. Now consider this case. These are the given keys using double hashing, and h1 is this k mod 10, h2 is k mod 8. See this is 8. Why it is 8? It is 8 because m is 10 and it is m dash is less than m, right? So our formula is this. For first key 72, we apply this formula and we'll get this 2 location, and this 2 is because it is vacant. Initially everything is, all place are vacant, so we can simply store this 72 into at address 2 in a hash table. Then for this is 72, and then this is the step number 2. Then second key is 27. So again we apply this 27, guys. This is multiply. Okay, this is also multiply. So in this case it comes out to be 7. So 7th index in our hash table is again empty. So this key value which is 27, this is mapped to this address 7. So no problem in this case also. We'll stop. See this, for these steps number 3, 4, 5 and 6, in each and every step we'll store one of the we map one of the key 36, 24, 63, 81 onto the your hash table. In these 4 keys, for example, this, if you calculate 36, first probe you will get 6 will be available. 24 you will get address 4, so 4 will be available. 63 you get address 0, so 3 will be available. 81 you will get address 0, so 81 will be stored at location 1, right? So for these 4 keys no collision occurs. You simply put these values into the that function which we have defined and for double hashing, right? So then comes this key 92, right? Then comes this key 92, and when we calculate the address using the double hashing method, it comes out to be 2, right? And see, this 2 is already, 2 is location 2 is already occupied, so we cannot store this 92, this key 92 into the location 2. So we need to, what we need to do, we need to rehash with the value of I is equal to 1. See, here we have used value of I as 0, but now we'll use value of I as 1 because this is probe, right? So when you use probe 1, then you will get the address 6. So again, the address 6 is also occupied, right? Address 6 is also occupied. 36 is already stored, so you cannot store 92 in index 6. So again you need to rehash using the probe I is equal to 2. So see this, now we have used I, value of I is equal to 2, probe is 2, then we get a 0. So 0 location is free, so we'll store this 92 at this particular location. Now see, there are like for this 101, so there can be first, when we calculate for location for 101, then we have this address is 1, so 1 is occupied by 81, so collision occurs. Then again we check second time, so we have 6 is also occupied. See this, 36 is already stored, again a collision occurs, right? Then number of times you have to calculate the address of a given your given key value to find out a proper place to store, to map it into the hash table, right? Because number of collision may occur in a sequence, right? Before you actually find a empty space where you can store that particular, you can map that particular key, okay? And that depends on the now in this particular case, because we have chosen table size is equal to 10, right? And see, 10 is not a prime number, right? So had we chosen table size as prime number, right, m as a prime number, the performance will be improved, right? At least better than in our case when we have chosen 10, right? So size of the table, hash table also matters, right? It's a right. Then we have a certain advantage and disadvantage of double hashing. Double hashing, what we have is 2 hash function rather than a single hash function is used. The performance of double hashing is very close to the performance of ideal scheme of uniform hashing. See, uniform hashing means that your key values are mapped uniformly onto the table as compared to the clustering, primary clustering or secondary clustering. In both cases, what we have is most of the keys are mapped to one part of the table, right? But in case of double hashing, the keys are mapped uniformly to the your hash table, and it minimizes the collisions, right? So comparison of open addressing means we have discussed 3. One is linear addressing, one is in this linear addressing, quadratic probing, and double hashing. See, clustering in linear probing, clustering is there, quadratic probing clustering is avoided, right? Secondary clustering is there in quadratic and linear also, but in double hashing no. But number of probes, sequence, m is the size of table, the number of probe is m. Quadratic, again it is m. In case of double hashing, number of probes can be m square. Cache performance is best in case of linear probing, and in case of quadratic, cache performance lies between the double hashing and the linear hashing. In case of double hashing, cache performance is very poor, right? So conclusion is the main trade-off between these methods are that linear probing has the best cache performance, right? But the most sensitive to the clustering, because both primary clustering and secondary clustering problem is there. While double probing has poorer cache performance but exhibit virtually no clustering actually, and quadratic probing falls in between the previous two methods. Means in case of quadratic probing there is no primary clustering, but and cache performance is somewhat better than the double hashing, right? But secondary clustering problem is there in case of your um, in case of your quadratic probing, right? So thank you.